So this theorem 7.9, I find parts of this really useful. Especially part 1 and part 3 I find really useful. Especially part 3. It says the following: let G be a group, and let's take an element A and G where the order of A is n. Let's suppose the order is n. Number 1, A to the k, where k is a positive integer, equals the identity if and only if n divides k. That's useful sometimes. Number 2, a to the I equals a to the j if and only if I is congruent to j mod n. I don't find that one I don't use that one a whole lot when doing problems. The last one's super useful. The order of a to the k is n divided by the GCD of n and k. So actually your book has a slightly different result on number 3. I have a different result. Mine is more general and more useful than their result. So please, you can have a look at the book's number 3 for 7.9, but mine is much more useful. Stick with mine. It's better. So I guess I'm going to prove these 3. The third one is a little tedious to prove. The first and the second aren't too bad. They're pretty straightforward. You can just kind of follow your nose on the first. I'm going to notice, though, the first 2 are if and only if statements, so it'll take a little work. So proof. So in the background, we have let G be a group, and let A be an element of G with the order of A equal to n. So remember, when the order of A equals n, that means n is the smallest positive integer such that a to the n equals e. So that's not really something I'm going to, I'll just scratch it out. So that's scratch right. A to the n equals e, that's my scratch word. It's a little bit of scratch. Keep that in mind throughout this problem. N is the smallest positive integer such that a to the n equals e. That's going to come into play quite a bit. Okay, so we're going to start by proving 1. Use purple here. Number 1. We want to show an if and only if statement. Let's begin with the forward direction. So, suppose we're going to suppose a to the k equals e. The understanding here is k is a positive integer. So we can perform the division algorithm. Remember the division algorithm a long time ago, way back in our first unit. It's the first chapter, actually. By the division algorithm, we're going to take k and divide n into it. So what does that do? It gives you k equals nq plus r for some integers, q and r. Oops. Q and r integers, and r has to be specified to be greater than or equal to 0 and strictly less than n. So I'm just dividing n into k. I'm going to try to show that n divides k, so I'd like to somehow show that r is 0. Okay, so what does that mean? That means the a to the k on one hand, right, we know is the identity, and on the other hand, we know that k here, put it in red, right, that's nq plus r, this right here. So we can break that up as follows. It's going to be a to the nq times, or start with, a to the r. But wait a second, we can break this up into a to the n to the q times, or start with, a to the r. Now what's, didn't turn, there it goes. What's a to the n? Remember that a to the n here is e, right? This blue dude right here, a to the n is e. Because the order of a is n, right? Back here we know the order of a is n. So that's going to be the identity. So we got the identity to the q power, start with a to the r power. Now, well, what's the identity to the q power? The identity to the q power is just the identity. So we got the identity times a to the r, or started with a to the r, which is just going to give us a to the r. So what have we done? We've shown that a to the r equals the identity, right? If you look at this, here on the left we got the identity. Here on the right we have a to the r. So we have a to the r is the identity. Now focus on this. Notice that r is less than n. But n here is the smallest positive integer back here, right? N is the smallest positive integer, such that a to the n equals e. So can there be a smaller positive integer, r, that does this, a to the r equals e? No. So since n was the smallest positive integer, such that a to the n gives the identity, then r cannot be positive, right? Then r cannot be positive because r is smaller than n, right? Look at this identity. R is smaller than n. Cannot be positive. What does that force r to be? Well, if it can't be positive here, greater than 0, then it has to be equal here to 0. So so the only options for r is greater than or equal to 0. If it's not positive, then it has to be equal to 0. So thus r is equal to 0. So what does that mean? That means, let's go back to purple. That means, therefore, k equals nq, and rather than putting a plus r on the end, right? Back here we had a plus r. We don't need to write a plus r because the r is 0. So k equals nq. What does that mean? Hence, that means n divides k. And that's what we wanted to prove, right? We wanted to show that if a to the k equals e, then n divides k. So now we're going to go to the other direction. We're going to start with n divides k, and we're going to show a to the k equals e. This will be easy, this one. So the other direction. So we're starting with suppose n divides k, right? And we want to show a to the k equals e. So if n divides k, then that means then there exists, now n's a positive integer, k is a positive integer. There exists q in the positive integers, such that, let's say, k equals nq. So now what I want to do, I want to raise a to the k power, right? We want to show a to the k equals the identity, so let's raise a to the k. So we have a to the k power equals a to the nq, should have been red, in other words, a to the n to the q. Now, what was a to the n? Well, in the background, right? In the background, we have this fact right here. The order of a is n, so a to the n is e. So this right here is going to be e. And we're going to get e to the q, and e to the q is simply e. So what do we have? We have a to the k right here equals e. And that's what we wanted to prove. We wanted to prove that a to the k equals e. Oops, wrong color. Golly, it's not working. That's it, right? We wanted to show that. A to the k equals e. All right, number 2, we want to show if if and only if a to the I equals a to the j, if and only if I is congruent to j mod n. Okay. Okay, so I'm going to start with this side here. I'm going to call it the blue. A to the I equals A to the J. So let's suppose A to the I equals A to the J. Without loss of generality, suppose I is greater than J. Then that means I minus J is positive. So we got a positive integer. Right? I is an integer, J is an integer. So I minus J is an integer, and it's positive because I is bigger than J. Then what we can do to both sides of this equation, we can multiply by a to the negative j. So I'm going to take a to the I, and on the right, multiply by a to the minus j. Now remember, a to the minus j is a to the j inverse, or a's inverse to the j power, however you want to write that. This is going to be equal to a to the j times a to the minus j, which, okay, I don't want to write then, I'm going to write so. Oh, we have, I'll write we have. Which gives, so this is a minus symbol right here, so you're going to end up with, the property says you add the exponents, right? We had a property with adding exponents. It's going to be a to the I minus j. When you add I and negative j, you get a to the I minus j equals, on the right side, a to the j, a to the negative j, is going to be the identity, right? Because a to the j and a to the j, a to the negative j are inverse of each other, so that's going to be the identity. Okay? Now, if we use property 1 that we've just proven, then the order of a, which is n, divides this exponent, right? This is kind of like our k right here. Right? Remember, a to the k equals identity if and only if n divides k. So here I have a to the I minus j equals identity. So by property 1, I'll just call it, the order n has to divide I minus j. In other words, a is congruent to j mod n. And that's what we wanted to prove, right? We wanted to prove I is congruent to j mod n. Now we want to go in the other direction. We're going to start with I is congruent to j mod n, and we're going to try to prove a to the I equals a to the j. So other direction. So this was the forward direction right here. 2, let's do the backwards direction. So this time we're going to suppose I is congruent to j mod n. So unraveling that, that means n divides I minus j. So what does that mean? That means I minus j is a multiple of n, equals nm, let's say, for some integer m. So now what I'm going to do, I'm going to raise a to the I minus j power, right? We want to get to that. We want to show, well, we want to get to a to the I equals a to the j. We want to get to that, right? A to the I equals a to the j. So let's take a and raise it to the I minus j power. And that's going to be what? A to the nm. We can rewrite this as a to the n to the m. Of course, we know a to the n is the identity, right? It's the identity. A to the n is the identity. This is an assumption, right? The order of a is n, so a to the n is the identity. We've got the n identity to the mth power, which is the identity. So we have a to the I minus j is the identity. Now what we're going to do, we're going to multiply on the right both sides of this equation. So it follows that So I'm taking this equation, a to the I minus j equals the identity. We're going to multiply on the right, or star on the right, I could say, by a to the minus j. A to the minus, no, a to the j, just a to the j, not minus j, a to the j. That's just the ordinary j, not a minus j. It follows that a to the I minus j starred with a to the j equals the identity starred with a to the j, which gives the following. So here you can add the exponents. It's a property we've looked at, a to the I minus j plus j. And here on the right, the identity is times a to the j, is just a to the j. So when you add those exponents, this is equivalent to a to the I equals a to the j. Okay, that's the forward and the backwards directions. Do I have time to do the third one in this video? I'm not sure. I'm going to try. I'm going to try to do the third one. So the third one is a little tricky. It is a little bit tricky. So I'm going to go ahead and do it. So what do we want to show? We want to show here that this is not an if and only if statement like the others. We want to show that the order of a to the k is going to be a positive integer, is n divided by the greatest common divisor of n and k. This is tricky. I'm a little disappointed in the book because he didn't cover it this way. He did a more specific version of this. I did a more general version. Okay. So remember what our goal is. No, I'm not going to say what our goal is. I'll write it. We will show that the order of a to the k equals n divided by d, where d equals the greatest common divisor of n and k. Okay, so I'm going to start this by saying let d be the greatest common divisor of n and k. I'm just using that letter because I don't want to have to write the GCD every time. It's a little cumbersome to write that. That means, the greatest common divisor, that means then d divides n, and d divides k, It's a common divisor of n and k. So that means n is a multiple of d, n equals dm1, and k is a multiple of d, so k equals dm2, with m1 and m2 are positive integers, n is a positive integer, k is a positive integer, d is a positive integer, so m1 and m2 must be positive integers. And also notice that the greatest common divisor of m1 and m2 is going to be 1. Why is that? Why are m1 and m2 relatively prime? So remember the greatest common divisor of n and k is d. So we're taking out the greatest common divisor, so that means anything that's left in common. So we're taking out everything in common, I should say, between n and k by d, D is everything that's in common between n and k. So what's not in common is m1 and m2. So they're relatively prime. So keep that in mind. That's going to be important later down the road. And also, I want to write that, what do I want to write? N over d is m1. That's going to come in useful later on. So n over d is m1. Okay. So when you're showing something has order n over d, first you're going to show a to the k. When you raise it to n over d, gives you the identity. That's the first part. So first, we show a to the k raised to the n over d gives you the identity. That's the first thing we have to show, If we want to show a to the k has order n over d, we want to show that when you take a to the k and raise it to n over d, you get the identity. Let's do that. That's the first step. So note a to the k, when you raise it to n over d, what happens? Well, let's see. What do we got? We got a to the, what's another name for n over d? N over d right here is m1. So I'm going to write this as k times m1. Because I'm using a property of exponents where you multiply those exponents. It's a property we proved earlier. Okay, so what's another name for k now? Another name for k here is dm2. So I'm going to replace this k with dm2. So I'm going to have a to the dm2 times m1. So now I'm going to switch out the m2 and the m1. I'm going to have a to the dm1 m2. Okay? So I just switched m1 and m2. And wait a second, what is a dm1? Well, what's dm1? If you go back here, dm1 is n, so I'm going to have actually, this is a to the n raised to the m2 power, using reverse properties of exponents. But a to the n is the identity, right? A to the n is the identity because a has order n, so this is the identity to the m2, which is the identity. So what we've shown is that a to the k raised to the n over d gives you the identity. So that's the first step to showing you have order n over d. Now, just because you raise a to the k to the n over d power and get the identity, that doesn't mean that's necessarily the order. You got to show that n over d is the smallest positive integer that does this trick. So we want to show n over d is the smallest positive integer. That's what we're going to show next. We show. So now we show n over d is the smallest positive integer. That works. That does this. That you can raise a to the k2 to get the identity. Okay, so let's look at the smallest positive integer that does this. Let's just call it m. We're going to call this m. Suppose m is the smallest. There's a letter I haven't used. I use m1, I've used m2. This is just a general m. So suppose m is the smallest positive integer, such that this works. What do I mean this works? A to the k to the m gives you the identity. So m is the smallest positive integer that does this trick. A to the k raised to the n power equals the identity. So we're going to show that m is actually equal to n over d. We're going to show m equals n over d. That's what we're going to show. We show m equals n over d. So how will we do that? Tricky. Okay. So first of all, note the following. Because m is the order of a to the k, that means that a to the km equals the identity, right? This is just taking this equation and multiplying the exponents k and m. So a to the k times m equals e. So by number one, what number one am I talking about? I'm going back here. Number one. So rather than a to the k equals e, I have a to the km equals e. A to the km equals e. So that means n divides km in this case, right? So by 1, km. Sorry, n divides km. N divides km. The order, right? The order divides km. n, if I can get this. It's not working. There it goes. Yeah, so number one said if a to the k equals e, then n divides k. Well, this is a to the km equals e, so n divides km. Okay, so what does that mean? That means, unravel the definition of divisibility. That means then km equals n times some integer. N times, let's say s, for some integer s. And these are all positive, right? These are all positive integers, so s is going to be a positive integer. Okay. Now, what's another name for k? What's another name for k? Let's go back and check what k was. K was dm2, right? I'll make it blue here. K right here was dm2. So that means, so we have, so in place of the k, I'm going to put dm2. And then we have a m equals, now what was n? N, if you remember, was here, dm1. And then we have an s. And that implies, divide both sides by d here. These are just positive integers. You get m2m equals m1s. Now there's a very important fact back here that we talked about a little while back. Let me see. Right here. The greatest common divisor of m1 and m2 was 1. They were relatively prime. Remember we said they have nothing in common. m1 and m2 have nothing in common because the d's, the greatest common divisors, divided out. So that's very important. So these are relatively prime right here. Very important. That's going to come into play in just a moment. Okay, so first of all, notice that m1, so first, note that m1 divides m2, m. Right, m2m is a multiple of m1, so m1 divides m2m. But here comes into play the relatively prime part. So because these guys are relatively prime, so since m1, let me just say, since the GCD of m1 and m2 is 1, since they're relatively prime, since the GCD of m1 and m2 equals 1, then that means that m1 cannot divide m2, m1 has to divide m instead. This goes back to our number theory stuff. Way back in chapter 1, there was a theorem that said this. Okay, so m1 divides m. Now what does that mean exactly if m1 divides m? Well, these are positive integers. Positive integers. It follows that, okay, let me erase this. Famous theorem. The absolute value of m1 is less than or equal to the absolute value of m. Right? If something divides something else, the absolute value of the one on the left is less than or equal to the absolute value of the one on the right. The absolute value of the one on the right is m. Because it's positive, the absolute value of the one on the left is m1. So m1 is less than or equal to m. Okay, so what we've done, we've found a positive integer, m1, positive integer m1. Right, that's what n over d is. N over d is m1. Remember where that was? Right here. We found a positive integer, m1, also known as n over d, that we were able to raise a to the k back here to that power, that's the m1 right there, and get the identity. And this is less than or equal to m, but wait a second, m here was supposed to be the smallest, right? M is supposed to be the smallest. So we also know by the minimality of m, we have that also m must be less than or equal to m1 because m is the smallest. That does the trick. So we have m1 is less than or equal to m, and m is less than or equal to m1. So therefore, in fact, m equals m1. And what's m1? It's just n over d, or n over the GCD of n and k, you could call it. So we have proven, hence, the order of a to the k is m1, which is n over the GCD of n and k. Proof. Done. So know that formula. Know that formula. You don't have to know this proof. This is a somewhat tricky proof, but know that formula. Okay, so we'll actually work a problem or two using this.